Okay, so this is section 3.5, Calculus 30, and we're talking about related rates. Now, we've done 3.1 and 3.2, which are very basic first and second derivative lessons. We've done a few chapters since now, and now we're getting back to 3.5. So we're coming back because I find that later in the semester you guys are a little bit more ready for this type of problem. So with a little bit more experience under your belt. I think related rates can be a little bit tricky, but if you follow the steps that I'm going to outline today, then I think it should be fine. I think you guys should be able to have no problem with it at all. Okay, so let's first of all take a look at what related rates are. So obviously we have rates plural. Okay, now when we talk about rates, that's rates of change or derivatives. Okay, so this is multiple derivatives. And these derivatives, or these rates of change, are going to be related in the context of the question. So let's read here what it says in your textbook on 3.5. In related rates problem, we are given the rate of change of one quantity and asked to find the rate of change of a related quantity. There's the related rates, okay? So you're given one rate of change and asked to find another related rate of change. So if you've taken a look at 7.4 already and done and looked at some of those examples, we have two rates in the same question, right? We have two different derivatives. So to do this, we find an equation that relates the two variables together. So we need to have an equation that relates the two variables in the problem. And then we use the chain rule. Obviously, we can use all the rules. We can use the power rule and the quotient rule and all these different rules to differentiate. But we differentiate both sides of the equation, okay, with respect to time. So this is where it gets a little bit sticky. And I think you guys have had some experience with respect to time. But all of that means is we can differentiate volume with respect to time. That means what is the rate of change of the volume as time passes, right? Or what is the length of the balloon string if you let it out? What is the length, the rate at which you let the string out over time, right? So it's just with respect to time. All that means is that the preferred variable, and I talk about the preferred variable a lot, right? Like if it's dy dx, the preferred variable is x. That means that whenever you run across an x in the equation, the derivative is 1. Or if it's, if it's dy du, whenever you run into a u and you take the derivative of a u, it's 1 because it's a preferred variable. Well, now time is the preferred variable, so the derivative of volume would be v prime, or the derivative of the radius would be r prime. Derivative of the height would be h prime. The derivative of the length would be l prime, and so on. Nothing is now 1 when you take the derivative of it. And that allows us to do these types of problems. Okay, so let's take a look at an example. Okay, here's example 1. And you might want to just jot this one down. I think it is in your textbook, but if you want to jot down some of the important information anyways that I'm going to highlight here. So for your notes, you might want to jot down this. We have a spherical snowball. It is melting, okay? A spherical snowball is melting, such that its volume is decreasing at a rate of 1 centimeter cubed per minute. Okay? So we've got the picture in our minds, right? We have this snowball that we're going to assume is a perfect sphere, and it is melting. Now it is melting, it is getting smaller in every dimension, and its volume is decreasing at a given rate. So you're going to be given a rate. So here is decreasing. This is the volume. So I'm going to write this. I'm going to write Newton notation because it's just I like it. So the volume is decreasing by 1. And the units are okay to write. I don't want to be too sticky on writing the units at the beginning, but it's decreasing. That's where the negative comes from at 1 cubic centimeter per minute. So the volume is decreasing because the overall size is decreasing in every dimension. Make sense? Okay. It's melting. It's getting smaller. So we're given a rate. Now, here's the other part. At what rate, so it's a question here, what rate is the radius decreasing? Okay, so here, we'll stop right there. Here is the rate of the change of the radius. We don't know what that is. So you're going to be given one, and you're going to be asked to find one. Those are the first two things. The third thing in every question like this will be, it'll tell you at a certain point in this whole process when you want to find this specific rate. Okay? So for example, the radius might not be changing uniformly over time. The radius might be changing very slowly at the beginning. And then as the snowball gets smaller, the radius might be changing quite a bit as it comes to nothing, you see? So that how this radius changes varies over time. So it's going to have to say, at the exact moment where the radius is exactly 5 centimeters, tell me exactly what the rate is right at that moment. So there'll always be a third part, and I usually just write it like this, at r equals, and then whatever the value that they give you, 5. Okay? So the volume, the rate of change of volume is constant throughout this whole process, throughout this whole question. It's constant. The radius changing may not be, so that's why they have to tell you, find me the rate of change at exactly 5 centimeters. Okay? So that's the first part of related rates problems. Given a rate, asked to find a rate, and when or at what point in the question am I now engaging all this stuff and getting my answer. So I am going to just throw up a little graphic here now. Well, it's not a graphic. I got a couple examples, but I'm gonna copy this here now, and these are my steps. Okay, and I didn't want to bring these in too early to overwhelm you, but I may as well bring them in now. What was that? Okay, well, let's just try this again. Copy that. Okay, so when you see these steps, you'll start to understand, hopefully you'll understand a little bit about what we're doing here now. So, okay, all right, so steps for related rates problem solving, and we're already just kind of getting into it. So the first one is read and understand the problem. Okay, what are you given, and what are you asked to find? And we've identified this. We're given the rate of change of volume. We're asked to find the rate of change of the radius. Because we understand that this radius will be changing along with the volume. It's not going to be the same number at all. The volume will change at a certain rate. The radius will change at a different rate. Draw a diagram if possible. Okay, that's a good, you don't have to, but I think it's always a good idea. Introduce notation. So we've set V as volume and R as radius. We've set V prime as the change in volume and R prime as the change in radius. The Leibniz notation, just for curiosity, is going to be this. dV with respect to time. It's going to be dV dt. This is going to be dr dt. Okay? But you don't have to use that notation if you're uncomfortable with it. No, I'm fine if you don't. All right, so introduce notation, often two variables for the two quantities. Okay. Express information in terms of derivatives. We've done that as well because a rate of change is a derivative of that quantity. So if the volume is changing, that's a derivative. Okay, so we're at step 5 in this. Step 5 says write an equation that relates all the information together. Okay, so what information are we given? Well, volume and radius of a sphere. Okay, so sometimes in these problems, it's going to be an equation that you know of from math classes previous, right? The volume of a sphere, okay, has a volume obviously, and it has a radius in it obviously. Okay, so that's going to be good, and that's the one we're going to use here. So volume is. Do you guys remember what the volume formula for a sphere is? We've got one now. Anything else? Any guesses? 4/3 pi r cubed. Thank you for finding that in the textbook and reading it. Good job. Okay. All right. So this is who you're gonna want to remember this one. Okay. Study this one again. Okay. Volume of a sphere. Oh yeah, I know. It's terrible. It's terrible. Oh, calculus is so hard. Sorry, it's not calculus. It's not calculus. All right. So here's an equation that relates all the information. So that's great. Guess what we're gonna do now? we are going to now differentiate both sides. And here is a word of caution, okay? Word of caution. We are not doing anything with this until later, okay? This is one of the steps. I note this later on, but you do not, please, I repeat, do not put 5 in here right away at the start and try and take the derivative with only one variable. Guess what you're going to get? The derivative of a constant is 0. It's not going to be much of a question. So you can't put that in there, okay? You put that in there later in the process. So this, just ignore that for now, okay? So now we differentiate. Oh, what's the derivative of v with respect to time? V prime, okay? What's the derivative of 4/3 pi r cubed? Well, if you notice, this is a constant, 4/3 pi. Okay, pi is not a variable, it's a constant. So we're going to do 3. This is going to come down and multiply by the constant that we already have. Right? And then this is going to be r what? Squared? Okay. And because we've taken the derivative of the right side with respect to time. So r is not our preferred variable, so guess what? I have to do chain rule. Remember it said chain rule back here? Chain rule? It's important. So I do this, but I have to multiply by r prime. Okay? Anybody freaking out right now? Or are you okay? You're good. Thumbs up over there. Okay, good. Anybody else? Thumbs up? And a hesitant thumbs up. Awesome. Okay, good, good. We're doing great. Okay. Okay. So differentiate. So there's no preferred variable. Everything is prime. Nothing turns into 1. Okay. All right. So now we substitute the information into the derivative. Okay. Here's a note: don't insert lengths or anything like that before differentiating. That's a common mistake. So that's my note about this whole R5 thing. Okay. So v prime. Am I given v prime? Yes. It's -1. Okay. 3 times 4/3 pi is just 4 pi. What is r? Oh, at this point that we are examining, r is 5. Now you can put r in. Okay? So at this snapshot of moment in time, we know that r is 5. But we don't know what r prime is, and that's actually what we're trying to figure out. So now we just solve for r prime. We solve. Everything else is numbers, so we've got -1 over 100 pi equals r prime. Okay. So as far as this goes, you can leave it like that. Just leave it in terms of pi. I think I got that right. Right? You're all good with that. So r prime. So that's what r prime equals. So now you want to finish off the question. It's a word problem. So you say the radius is changing. Blah blah blah, write it as messy as you can, like me, at a rate of. So now we have to make sure we include our variables here. Okay, and what's our variables there? What were we given in the question? Something per minute, right? Centimeters per minute. So the volume was centimeters cubed per minute, so the radius is just going to be centimeters per minute. Okay? Okay, just circle your answer or identify your answer, make sure you got your units in there, and we're all good. Okay? So that is example number 1. That's intro to related rates. Do any of you have any questions? You ready for another example then? Awesome. Okay. Here's another example. I'll give you a second to copy this down. Again, it is in your textbook, but it might be good to have just a quick version of this. Draw that diagram as well, and we'll get to it in a second. Okay, so I just brought the steps, okay, for solving related rates problems here on the side, so we can refer to that as we go through. So this example 3 says this: a spotlight on the ground shines on a wall that's 10 meters away. So this right here, right, it's not shown in the picture, but that's 10 meters away. Okay. A man 2 meters tall, so this height right here is 2 meters, walks from the spotlight towards the wall at a speed of 1.2 meters per second. Okay, so his distance, right? Now remember, so this is a rate of change, right? Because we've got a meters per second. That is a rate of change. It's distance per time. So that's going to be some kind of derivative, right? So what is it going to be the derivative of? Well, what is changing? What's changing is this guy's distance, right? So the diagram already has an x here. So this here to the man's position is x. So x prime, the derivative of x, the rate of change of this man's position as he walks, is 1.2. I'm going to drop the units for now until the end, okay? And it's positive, whatever. Okay? Okay? So there's rate number 1. How fast is the shadow on the wall decreasing when he is 3 meters from the wall? Okay, so how fast is right here, the shadow on the wall, and they've already got that labeled as y, because you see this dotted line here? His shadow is this big right now, right? And there he is, he's walking. Okay? That's him. Okay? That's his shadow. It's pretty scary. Don't look too close, okay? It's not an accurate representation. I think that's pretty darn good, actually, for a math guy, okay? But I will erase that now so it won't distract you. But picture this, right? As this man, okay, so here he is, this exact man right here, okay? There he is. How about this one? It's pretty good, right? See? Okay, there he is. He's walking. He's got his hand there. It's pretty cool. When he's over here at this position, look, his shadow is smaller on the wall. Makes sense, right? You get closer to the wall, your shadow gets closer to your very height when you're right at the wall. Makes sense, right? Okay, you with me? Yeah. Focus. Okay. So look at this. This is amazing. This guy's changing, a rate of change right here. Hey, x is getting larger. Guess what? The shadow is getting smaller. So y prime, we don't know what it is. It should be decreasing. So at the end of all this, y prime should be negative, right? Okay. So y prime, we don't know. Okay. The third part is, at what point in time are we going to calculate this? Well, we're going to calculate this at 3 meters from the wall. So 3 meters from the wall. Okay? So what value of x, because you can't just say z equals 3. Don't introduce another variable there, okay? Let's keep with just 2 variables, okay? So when he's 3 meters from the wall, how many meters is he from the light? 7, right? 10 minus x. So if 3 is 10 minus x is 7, right? So this is at x equals 7. So you kind of got to just think through logically a little bit. Okay, so when he's 3 meters from the wall, the light's 10 meters from the wall, so he is 10 meters from the light. Here's the x equals 7. Okay? At x equals 7. So again, that's going to be tucked away for a little bit later. Okay, so we've understood the problem. Awesome. Draw a diagram. Given. Thanks a lot. Introduce notation. Why not? X and y. It's already on the diagram. Thanks again. Introduce or express the information in terms of derivatives. Oh, okay, good. Yeah, x prime, y prime. Awesome. Write an equation that relates all the information. That's where we're at. All right. Now, sometimes it's not as just a volume formula or something like really, easy, like you took a look at in elementary school. Sometimes you just kind of have to look at the situation and say, hey, I need to just write any equation here that relates x and y in the situation that's given. So, anything jump out at you here? Trying to look at the solution in the book. Anything jump out? Okay, I wouldn't think about an angle or anything. Let's not introduce a third variable, theta or anything. Don't worry about that. What you should see is we have some similar triangles here. Okay? We have some similar triangles. Because the wall is upright, the man is upright, we have parallel situation there. We have the same angle, right? So we have this little triangle right here, where this is 2 and this is x, right? And we have this larger triangle here that's similar, same shape, where this is y and this is 10. See that? So similar triangles, we can write a simple proportion equating the ratios of corresponding sides of similar triangles. Okay? So this is one of the things that you want to keep in mind, one of the tricks to write an equation. So, and you can do this however way you want, doesn't really matter. You could go 2 over x equals y over 10. You could go x equals 10 equals 2 over y. You could go y over 2 equals 10 over x. Doesn't matter at all. Okay? So I'm just going to write this out here. Let's do it maybe up here. So let's go this 2 over x equals y over 10. Okay? Let's just pick one. Doesn't really matter. If you did something different and you want to try that, you go right ahead. The differentiating part, you might use some different rules, either product or quotient or whatever to differentiate. Maybe a power rule there. But as long as you get an equation there, it should be fine. So this relates to 2 variables. Awesome. Differentiate both sides with respect to time. Now, I don't know if I like, do you like x in the denominator there? I don't know if that's great or not. I mean, if you want to get y by itself, so it is more like a y equals situation, I don't know. You could do that if you want. You could rearrange this before you take the derivative and go y equals 20 over x. You could totally do that. Or you could do this. You could do xy equals 20, right? You could do y equals, don't write all this down if you don't want to, but you could do this. So you could take the derivative of this equation using the maybe quotient rule over here, eh? You could take the derivative of this one using product rule over here. You could take the derivative of this one using the power rule over here. So, you know what I mean? You got options. And you know how to do all those rules, so it shouldn't scare you. You get the same answer. So I'm going to probably do this. What's going on? Do this one here. So, just because I like y equals and I'm not afraid of a negative exponent, hey? Who's afraid of the big bad negative exponent? Nobody. Okay, so y prime, right, for taking the derivative. Now over here, power rule, no problem. Negative 1 comes down here, we've got negative 20. X to the power of negative 2, no problem. X is not my preferred variable. Chain rule says I got to do what? What do I have to write here? X prime. You guys are awesome. Easy, huh? Easy. Now you don't have to simplify anything. You don't have to. Just one step of differentiation right there. You don't have to stress out about simplifying anything. Because now we're on to step 7. Okay? That was 6. So now 7 we're on, and we're going to fill in some values. You're going to be given some values. You might have to, when the questions get a bit tougher, like in 7.4, you might have to do some side calculations. I helped you with the question earlier today, right? So you might have to do some side calculations to find another missing piece. Don't be afraid of that. Right now I think these are easy enough that you're given what you need, but let's see. So y prime, trying to find. Good. That's awesome. Let's just leave that there. Negative 20. Now, do we know what x is in this point of time? Yes. X is 7. Okay, and we've already done this, right? We've already figured that out. 10 minus 3 is 7. So we've already figured that out. That's to the negative 2. X prime is 1.2. So you just fill everything in, and then you evaluate it. Okay? So what do you got? Negative 20 over 49 times 1.2. What does that give you? You got that on your calculator there? Be about negative, I've got 24 over 49, which in decimal is what? Pretty much half? 20 decimals. No, 3 or 4. 0.4, 8.
4, 8, 9, 8.
Okay. Okay. Oh, yeah, negative. Yeah, got negative. Okay. So, units now. Okay. Units. This y, okay, is going to be, it's a distance. What distances are we talking about? Oh, meters, right? Okay, meters. And then, is this going to be, it's a rate, so meters per, well, I guess we differentiate with respect to what? Time, right? So, it's going to be meters per second. Yeah, that's right. Okay, so here you go. You've got your really your exact answer and your approximate answer. Make sure you keep your sign, your negative there. That means it's decreasing. Now you could say the rate of change is negative 24 over 49 meters per second. Boom, done. Or you could say the shadow is decreasing. Use your words for the negative. Decreasing at a rate of 24 over 49 meters per second. So either of those are okay. Probably not going to want to say it's decreasing at a rate of negative. Don't do double negative, but you know what I mean. The rate is this, negative something, or it's decreasing at. All right, so there's intro to related rates and 2 examples. I have more examples that you'll be able to see on other videos, and we can certainly take a look at your homework or problems that you run into. Here's the steps one more time, and that's your lesson on 3.5. Any questions related rates?